Hi, I'm Bonnie Ng, and this is my final project for CSCI E222 Foundations of Large Language Models at Harvard Extension School. My project is called Generating MD&A Prose from Financial Tables Using LLMs. And the core idea is a four-stage style transfer pipeline that takes a raw financial table from an SEC filing, converts it to an MD&A write-up required by the SEC, and then translating that to a plain English summary that any layperson can understand. Let me walk you through the problem, the pipeline, the results, and what I learned. In my day job, I'm an accounting controller. Part of my job is to produce and review management discussion and analysis section of a company's SEC filings. An MD&A is the narrative explanation of the financial results that accompanies a company's financial statements every quarter. There are two problems that motivated this project. Firstly, producing an MD&A is very labor-intensive. A typical write-up takes weeks of effort from various finance teams. We have to translate the spreadsheet data into structured, formal prose and go through layers and layers of review and checks. Secondly, once this is written and published, very few people actually enjoy reading it. The writing style of MD&A tends to be very formal, dry, and often full of accounting jargons. This is done partly to ensure that we're being very factual about the financial results, but it also creates unnecessary friction for an everyday layperson who wants to just read the financials and understand how a company is doing financially. This project tries to address both, to automate the translation from table to MD&A, and then to simplify that MD&A into plain English. This project uses the TAT-QA dataset, which stands for Tabular and Textual Question Answering. It is a dataset built from real SEC filings, and it was published at the ACL in 2021. In this dataset, each context is one unit. A context includes one financial table from a 10K or 10Q, paired with at least two MD&A paragraphs that describe the table, and multiple human-authored question-answer pairs about the context. The dataset has about 2,756 contexts and over 16,500 Q&A pairs. What makes the TAT-QA interesting and challenging is the mix of answer types. About 43% of the answers represent span extraction, which means finding the right words and information from the context. But 42% of the answers require arithmetic computation, which means the model has to actually compute an answer from the numbers in the context. This is a very different skill from text extraction, therefore we need fine-tuning rather than just prompting. And here's the full four-stage pipeline. Stage 1 is where we fine-tune a language model. We use Google's FLAN T5 extra large with LoRa to answer financial questions from tables. This is the core training step. Stage 2 is inference. We take that fine-tuned model and run a fixed set of 8 standard financial questions through it for every table in our demo set. The output is an insight bundle, which is a structured set of question-answer pairs capturing the key financial facts from the table. Stage 3 then takes that insight bundle and uses Claude's Sonnet 4.6 to render it as a formal MD&A paragraph. We'll be using few short examples from real SEC filings in the dataset to establish the right style. Stage 4 is a second call to Sonnet to simplify the formal MD&A into plain English. One important design principle is that each stage is independent. That means we can isolate the errors in each stage and improve them separately. This also means that errors from an early stage will propagate into a later stage if it's unchanged. I'll come back to this when we discuss limitations of this project. And I'm going to switch over to the Jupyter Notebook now to show you the configuration. In here, you can see the training setup, and we're using FLAN T5 extra large, which include Google's 3 billion parameter instruction tune encoder decoder model. We chose extra large over the large variant because the larger capacity meaningfully helped with multi-span questions, which require coordinating multiple facts simultaneously. We have confirmed this through various ablation experiments across different permutations. let's go to section 3 of this notebook. In here, you can see that we are going to be, rather than fine-tuning all 2.85 billion parameters, we'll be using LoRa, which stands for low-rank adaptation. LoRa adds small trainable matrices to the attention layers, which give us about 37.7 million trainable parameters. Let's see, it's included here. Yeah, so this is only about 1.3% of the base model. This training ran overnight on my Mac Studio using Apple's MPS backend, and the training took about 6 hours to complete. Let me scroll down to show the actual training. Yeah, so this took about 6 hours to complete. In addition to that, we added a chain of thought targets for arithmetic questions in the training data. Let's switch over to that section. So in here, we, instead of just training the model to output, let's say 1.4, we train it to output calculation, and then we include the derivation and the answer. By including the derivation step, the model is trained to reason rather than just guess the answer. This has improved the arithmetic performance. Now let's go back to the slides. All right. And here are the results from stage 1 evaluation on about 500 validation examples. The fine-tuned model achieves token F1 of 0.399, which is about 197% improvement over the baseline pre-trained model. And the Rouge L score went from 0.199 to 0.395, which is roughly doubling. The more interesting results is by answer type. For arithmetic, the baseline model scored only about 0.003, which is essentially 0. After fine-tuning with chain of thought targets, it reaches 0.403 here. This score is still low, but it's still a qualitative shift from the pre-trained model that couldn't reason numerically at all to one that can. And we can see that for multi-span, it also improved by, from 0.149 to 0.606, which we know is from the capacity from the extra large model. These numbers are still below the latest results from the TAT-QA leadership board, which used very specialized symbolic execution that runs Python code to compute arithmetic answers, which is likely a better approach for arithmetic operation than fine-tuning a model to generate text. Nonetheless, our fine-tuned model generated a almost 200% improvement over the pre-trained model, which is still helpful. Let's switch back to the notebook and take a look at the output. So in this section, the pipeline gets quite interesting. Let's take a look at the actual output over here. So you can see that the financial table, the underlying financial table here, this is the real table from a TAT-QA context, which shows sales by contract type for 3 years. And the fine-tuned model runs our 8 standard questions against it and produces this insight bundle. And you can see that some answers from the insight bundles is good. For instance, it correctly identifies the gross profit figure, which is 1107.7 million, which is the figure here in 2017. However, it picked the wrong year, and also the mathematic calculation is incorrect. For instance, when we look at the revenue change, the model says calculation 1496.6 minus 1202.9, answer being minus 236.5 million. This is incorrect because the even though the chain of thought format worked, by showing the derivation, but the actual computation is incorrect. If you look at the source table, the sales actually increased from 2018 to 2019, not decreased. The model got the operands in the wrong order. And let's now take a look at section 6. So here you can see that the Prose generated from that insight bundle. If you just read the prose, it actually is convincingly formal. It says net revenue decreased by 236.5 million, or approximately 29.7% compared to the prior period, declining from 1496.6 million to 1260.1 million, primarily driven by increases in costs and expenses across multiple categories. So this reads exactly like an MD&A in an SEC filing, but unfortunately it reported the wrong numbers because the stage 2 of the model generated the wrong insight bundle, and therefore the style transfer worked, but the style transfer in stage 3 worked, but this extraction in stage 2 was not always accurate. And let's go back to the slide and look at the readability shift. The generated MD&A scores a flash reading ease of 29.2 and a flash Kincaid grade level of 13.1. And the real TAT-QA reference paragraph scored 28.6 at grade 15.3. This means that our generated MD&A is within 2 grade levels of the real SEC filing language. The style replication is working almost exactly as designed. And then in stage 4, we used another prompt to instruct the model to write for a general audience, taking that prose from grade 13.1 down to grade 8.2. That's a drop of 5 grade levels in a single API call. And the flash readings ease jumps from 29 to 63 from difficult to standard readability. That means the style transferred from a text that required a postgrad level to a high school student level, which achieves our goal of the project. For stages 3 and 4, we used 4-metric evaluation for evaluation because Rouge is not the right measurement for style transfer. You can see here that Rouge-1 was only 0.216, and it's essentially 0 for Rouge-2. When you're paraphrasing, the bigram overlap should be low, so these scores are reasonable. But on the other hand, the BERT score is 0.729, which means the MD&A prose captures the semantic similarity more faithfully, and readability is the primary quality signal. In addition, when we look at the factual consistency based on the fraction of numbers in the generated MD&A being traceable to the insight bundle, the score is 0.846. And this means that about 84% of the numbers are verifiable against the insight bundle. The remaining 16% is likely include some formatting differences and some derived calculations, and perhaps some genuine hallucination. The biggest limitation of this project, the error propagated from stage 2 and the exclusion of the paragraph context from stage 1 inputs, which hurts the span answers, and the need for human review before any of the generated results go into an actual filing. The system is a drafting assistant instead of a fully automated production tool. In conclusion, to summarize, we built a 4-stage pipeline that runs entirely on the Mac Studio, achieving a close to 200% improvement in token F1 over the pre-trained model, and a generated MD&A style that matches SEC register with 2 grade levels, and a plain English output that is 5 grade levels simpler. The most obvious future improvement for this project is in stage 2. We should add paragraph context to the inputs, which should help with span answers, but that would take significantly more compute. Enterprise solutions should also consider implementing deterministic calculations from source table to feed into the MD&A prose, which would guarantee correct numeric reasoning. The most important lesson from this project is the pipeline design. By designing each stage independently, any errors and design changes in each stage can be isolated. However, upstream errors could also propagate downstream. Thank you. The full code is in the Jupyter notebook, and the link to this video is on the slide.